Welcome back, students. In this lecture we will see how to draw inference line diagram for reactions in an indeterminate beam. So we have already seen the methods of drawing inference line diagram. So we will be seeing the equilibrium method of drawing ILD here, as we require a quantitative inference line diagram, right? So the method is basically you have to place your unit load at every possible points on the beam and compute the value of reaction at each of the point. So it is to be noted firstly that since the beam is indeterminate, we will be first drawing the ILD for the redundant reaction, right? So out of, say for example, here we have a two-span continuous beam, so there are three unknown reaction: vertical reaction at A, reaction at B, reaction at C. So out of this we have to choose one as redundant, and first of all we will draw the ILD for the redundant reaction. So once the ILD for redundant reaction is drawn, you can relate this redundant relation with reaction with the reactions other than redundants and find out the ILD for those reactions as well, right? So the method is you will have to place unit load at every possible points in the beam and compute the value of the redundant reaction, and then if you plot all this value of resultant at the corresponding points of unit loads, you will get the inference line diagram, right? So if you have to do that, you'll be doing this. So by placing a unit load at any point, and you have to find out a reaction, unknown reaction which is redundant, you can do that by force method, which is one example is actually method of consistent deformation, right? So, consistent deformation method, say this is the example: two-span bridge, load is positioned at, say for example, D, which is the distance of X from E maybe, right? So D is any random point, right? So what we do is actually we'll first of all say that we are drawing for reaction at A, say AY. Okay, so what we do is we'll consider this reaction at A as redundant, so we'll remove that support and make it a least out primary structure. Okay, so remove the support at A, it is a primary structure, applied the external loading, you find out what is the resultant displacement at A. Let's name it FAD, the displacement at A due to loading at D, so it is FAD, right? Now on the same release structure, what we do is we'll apply a unit force corresponding to the redundant, so I get a displacement FAA at that point, right? Displacement at A due to unit load at A, so that is FAA. So actually at this point there was a redundant reaction which was AY, so if you apply that AY, you will get the total displacement to be AY into FAA, right? So you can consider the compatibility condition at A, which was actually total displacement at A was 0. So now here we have two displacement, which is FAD and AY into FAA. So if you add both of these, it is going to be 0 as per the compatibility condition, right? From here you can get what is the value of AY. So if you want to find out the value of reaction at A when the loading was given at D, the formula will be minus FAD divided by FAA. However, it is to be noted that when unit load was placed at D, the displacement at A was FAD. Similarly, if you place a load at A, the displacement at D can be said to be FDA, which is displacement at D due to load at A, right? So if you compare this diagram and this diagram, according to Maxwell's theorem of reciprocal displacement, you can say that FAD is equal to FDA, right? Unit load placed here causes a displacement of FAD at D, the same unit load placed at A will cause a displacement of FDA, and both has to be same, right? But only problem is both the displacements are on the opposite direction, hence you get to put a negative sign. So you can, instead of FAD, you can substitute it as minus FDA. So you get AY value as FDA divided by 1 at AA, right? So this is the method. Now you can, instead of D, you can place it at a new point. Say you can place it at some more away. The unit load can be placed somewhere away. Say it is E. So if you want to know the value of ILD or ILD ordinate for AY at E, it is going to be FEA divided by FAA, where FEA means displacement at E when a unit load is caused at A. So it is going to be somewhere here, FEA. This is going to be FEA, right? So by this method you can find out the displacement at any point. Now the validation of the method, Moeller-Breslau theorem, the same thing we have done already. Like, what does Moeller-Breslau principle say? If you want to compute the reaction ILD for this RA, you remove that, so release this point, apply a unit force in that direction, find the displacement. So you removed the support here, applied a force corresponding to AY, which is unit force, and you find out the displacement. So displacement is going to be something like this. Okay, and once you compute finally the what is ILD for AY, you can see that the ILD also will bear the same shape as this, but only thing is there is a scale factor of 1 by FAA, that is you have to multiply this deflection with 1 by FAA. So with that background, now let's see an example. Here we have a propped cantilever. Support A is fixed and support B is a prop support, which is simply supported. Okay, we have constant here, and they are asked to find out the numerical value of ILD for reaction at A, vertical reaction at A. AY has to be found out. Okay, as you can see, there is one reaction here which is BY, and since the beam is fixed, there is going to be a moment as well. So 3 reaction, 2 available equation, written the beam is indeterminate to 1 degree, right? So the indeterminacy is 1. Since we have to find out the inference line diagram for vertical reaction at A, we can consider vertical reaction at A as redundant, right? So what we do is we'll remove the beam's capacity to resist AY. So what has to be done at AY, that means that AY is free to move up and down. So we introduced a vertical roller at A, so it is possible to move up and down. Then what we do is we'll apply a unit force corresponding to AY, which means that we applied a unit force, say 1 kilopascal. So 1 is upward, acting upward along the direction of AY, which means that the reaction at B is going to be a vertically downward force of 1, because there is no other force acting, right? So if we apply 1 here, there is a result reaction of 1 downward. Okay, and this moment, sorry, this vertical reaction acting downward can create a moment which is clockwise, and the value is 1 into 18, which means that 18 clockwise. So in order to resist this moment, you have to develop a moment at this support, which is actually 18, which is opposing this, so it is anti-clockwise, right? So you already found out what is the reaction on the real beam. Okay, so what will be the ILD is like something, this is the qualitative shape of the ILD it is going to be, right? Okay, so now the aim is you will place unit load at different points, say somewhere here, every point in this, and you have to find out the value of reaction AY, right? So the method is, you can use the conjugate beam method. Okay, so if you quickly recap what was conjugate beam method saying, like if you want to find out the deflection on the real beam, all you need to find out is the bending moment at that point in the conjugate beam, and if you want to find out the slope at the on the real beam at any point, all you need to find out is the shear force on that point in the conjugate beam. However, you should be in a position to draw the conjugate beam, right? So how we do draw conjugate beam? So it's to be seen that if in a real beam the support is pin support, the conjugate beam also will be having the pin support at the same location. If real beam is having roller support, the conjugate beam is also having roller support. If the real beam is having fixed support, the real beam should be having free support. If the real beam is having free end, in the conjugate beam the free end will be replaced by a fixed support. So the whole idea of constructing a conjugate support is like, see here for example, at a free end we know that theta is a non-zero value and delta is also a non-zero value, which means that as per the conjugate theorem, in the conjugate beam the theta has to be non-zero, which means that the moment has to be non-zero, and theta has to be non-zero, which means that shear force has to be non-zero, and delta has to be non-zero, which means that moment has to be non-zero. So only support which can offer non-zero moment and non-zero V is this shear is a fixed support, right? So here we have a slider, and in slider theta is non-zero, and theta is 0, right? Slope is 0 and delta is non-zero. Delta is non-zero, which means that the moment here should be non-zero, which means that there should be some moment at this point, but theta equals 0, which means that there should be vertical shear should be 0 at this point. So only possible support which can think of is exactly the same vertical roller here in the conjugate, right? So now that we load the conjugate beam with the M by EI diagram of the real beam, so you have to draw the moment diagram of the real beam, which is nothing but an inverted triangle, something like this, right? With this value is going to be 18, the value this is going to be 0, and everything is negative, right? 1 into this distance, so 1 into 18 is 18, so it is in clockwise direction as per sign convention. This is the positive sign convention for bending moment, so clockwise on the right, which means that it is a negative moment, right? So this is the bending moment diagram for real beam, 18 at A, minus 18 at A, and 0 at B. So we load this bending moment diagram, M by E diagram, with the conjugate beam in the conjugate beam. Okay, so we drawn the conjugate beam. The pin support is replaced by pin support only. The sliding roller is replaced by sliding roller only. Then we apply the loading, which is nothing but M by E diagram of the original beam. From here, now you have to find out what is the reaction, which is nothing but the area of this triangle. So 18 into half into 18 by EI into 18. So 18 into 9, it is going to be 162 by EI. So this is the vertical reaction. This reaction and this force can create some moment, which is going to be 162 by EI into 18 minus 162, which is the resultant force acting at, say, distance 6, right? The resultant total area of this is 162 by EA, and it will be acting at the centroid. So 160, so 162 into 18, which is moment caused by the reaction, minus 162 into 6, which is the moment caused by the forces. So that will be something like 1944 by EI. Clear? You have to find out the deflection at each point on the real beam. Say like you have to find out the deflection at B, deflection at D, deflection at C, deflection at A. So as per the conjugate theorem, beam theorem, only thing you have to do is, if you want to find out the deflection, you have to find out the bending moment at that point in the conjugate beam. Okay. So from the diagram only it is clear that deflection at B is to be 0, right? Which can be clarified from the conjugate beam also, that at this point the moment is going to be 0. So delta B is 0, that is fine. Now if you take the second point, delta D, if you want to find out the deflection at D, delta D, so you have to find out the moment at D dash. From this diagram you have to find out empty dash, right? So it is going to be 162 into 6 minus area of this triangle, which is half into 6 by A into 6 into the distance to the center, which is going to be 1 by third of the base. So 1 by third of 6, which is 2. You get delta D is 936 by A. Okay. Then you have to move on to find out the deflection at C. So this will be the loading diagram. The value at this point is 12, so I marked as 12. So the deflection is going to be, so the bending moment at C dash, so it is 162 into 12 minus area of this triangle, which is half into 12 by EI into 12 into the distance to the centroid, which is going to be 12 by 3, which is 4. So computing, you have the value 1656.EI by EI. Delta A is going to be bending moment at A, which is nothing but 1944 by EI, which is already computed, right? So now we have got all the deflection. You can easily draw the ILD. So ordinates of ILD is going to be the deflection at each point divided by the deflection at A. So deflection at A is 1944 by EI. So each point deflection has to be divided by 1944 by EI. So if you do that, you can get the coordinates of ILD for reaction at A, which means that you get something like value like this. Value is 1 at support A and value is 0 at support B. In between you have some random value. So if you plot that, the ILD for, you can obtain the ILD for AY, and it is going to be a parabola. Fine. Now that you have got already the written ILD for redundant reaction, other reactions, say BY and support moment MA, okay, and use this ILD, which is already known. ILD for AY, which is already known, can be used for drawing ILD for BY. So you can say that a unit load is acting at a random distance x anywhere in the beam. So if you take sigma pi equal to 0, AY plus BY equal to 1, which means that BY is equal to 1 minus AY, which means that ILD for BY is going to be 1 minus ILD for AY. So you can find out the coordinates of ILD for BY here. It is 1 minus 1, 0, 1 minus 0.85 is 2, which is 0.148, and go on. If you try to plot that, you are going to get something like this, which is nothing but a parabolic spandrel. Okay. The next thing you can do is you can find what is the relation of MA with the other reactions. So if you write an expression for MA, it is going to be 18 into BY minus X into 1. You already know the ILD for BY, which means by putting the values of ILD of BY in this expression, you can get the values of ILD for MA. So if you substitute these BY values in this equation, you can get ILD for MA, which is going to be something like this. And if you plot that, it is going to be look something like this. Okay. So if you have considered more points, this is not going to be a straight line, it is actually curve. It is going to be a curve actually. Since the point is limited, that's the reason it is going to be look like a straight set of straight lines. It is not straight line, please believe it is a curve actually. Clear? That's it for today's lecture. In next lecture we will see how to draw LD for shear force, bending moments, etc.